Okay, so in this video we are going to start talking about measurements. Up until now we've talked about the SI system, the SI unit system, we've talked about order of magnitude, and we've talked about how to do unit conversions, both basic and more advanced unit conversions. Okay, so now we're going to move on to the main part of this unit, which has to do with measurements and uncertainties. Okay, and so on the slide you can just kind of see some of the topics we will be talking about. Okay, so in this video we're mainly going to be talking about those first three things, and then we'll probably do 2 or 3 more videos over the rest of this list. Okay, so to kind of do a lead into this topic, this idea of uncertainties, I'm going to show you a clip, and this clip is from a lecture at MIT. Now, this lecture is taken from a class called 801 at MIT. The professor's name is Walter Lewin. I watched a lot of his lectures when I was in high school to teach myself physics. And this clip is taken from the first day of class. 801 is a freshman level physics class that all students who go to MIT have to take. And so what you're seeing is not only a college lecture over physics, but it's also basically the first day of school for them. Okay, so I want you to keep 2 things in mind as you watch this video. Number 1, think about how is college different from high school, keeping in mind that this is also the first day of school for the students that you're seeing. And then second, related to the content of the video, what questions do you have about uncertainty after watching this video? Would the final result of his experiment be believable without knowledge of the uncertainty? Okay, so this video, I will put a link up into the video. You're going to watch between actually, you're going to watch from the beginning of the video up until 11:12, I believe. Actually, just to kind of cut down on the amount you have to watch the first minute of this clip and then skip ahead to 4 minutes and 35 seconds and watch up until 11 minutes and 12 seconds. Okay, and then after you watch this, the slide says to turn and talk with your partner. Obviously, you can't do that too easily, but I'm going to ask a question or two in Edpuzzle about this video. Okay, so go ahead, watch this video. I'll put the link up so you can watch this video, and then afterwards you can respond to the questions that you see. Okay, so hopefully you found this video interesting. Hopefully it gave you some insight both as far as what is college like compared to high school, and also about uncertainties and measurements, because it is something that you might not have heard about before in your past science classes. Okay, so with that being said, let's go ahead and move on in the notes. Please make sure that you're using good note-taking skills as we go through the slide. You should not be writing every single word, but you should only be writing the most important information on each slide. Okay, so first of all, we are going to talk about what is called an analog measuring device. An analog measuring device is basically a measuring device that uses mechanical means to make the measurement. Okay, so for example, a ruler is an analog measuring device. A meter stick or a yardstick is an analog measuring device. If you ever see a meter that looks like this, that has like a needle that moves back and forth, you might have one in your car that tells you how much gas you have or how fast you're going. Those are analog measuring devices, as opposed to digital measuring devices, which are usually done with electronics. Okay, now when it comes to making measurements with analog measuring devices, what you need to know is that on a good analog measuring device, you can estimate on the last digit. Okay, you can make an estimate on the value up to a point. Okay, now in the picture we can see, if we want to measure the length of this blue line right here, what we would see is, okay, so this is 1 centimeter. Okay, this is 1.1. And then this mark over here is 1.2. And I know that it's somewhere between 1.1 and 1.2. And so what I would say is that I have 2 certain digits in this measurement. Okay, I am positive about the 1.1. Okay, because I don't even see the 2 on the scale, and so I know it has to start with at least a 1 point something. Okay, I can also see that this mark right here is 1.1. and this mark right here is 1.2, I can say with 100% confidence that's somewhere between 1.1 and 1.2, and therefore I can write down 1.1, and both of those digits are certain. I am certain that they are correct. Okay, now because this is an analog measuring device, I can also estimate on the last digit, which is then going to be uncertain because it's a it's an estimation. Okay, so what I would say is, okay, well, it's between 1.1 and 1.2. It kind of looks like it's halfway, or more than halfway. So I would say maybe 1.17 centimeters. Or I could say 1.18 centimeters, and both of those would be equally valid because the 7 or the 8 would be an estimate. It would be uncertain. Okay, so in other words, here I've got two certain digits, and then the last one, the estimation, is what I would say is uncertain. Okay, because it is an estimation based off of my best judgment. Okay, and again, we're just talking about analog measuring devices right now. Pause it there if you need to look at that some more. Okay, so moving on. On the next slide, we have a picture, and we have two kind of analog measuring devices set up, and one of them has smaller tick marks than the other. Okay, now in both cases, we're asked to measure the length of a red line, and in reality, the length of the red line is the same, but the measurement that you come up with depends on the precision of your measuring device. So, for example, if I am trying to use ruler ruler letter A on the top, and I ask you, okay, what is the length of this red line? Okay, I start with what do I know for sure? What is my certain measurement? I know for sure it's between 1 and 2. Okay, that one is certain. But now I get into the uncertain territory, and now I have to make an estimate. Because when you make a measurement using an analog measuring device, you should make an estimate. And now it comes down to a judgment call. I see it's less than the halfway point. I'd say it's probably 1.2 or 1.3. And I'm going to go with 1.2 meters, keeping in mind that the 1 is certain, but the 0.2 is uncertain. And if I use ruler B to make the same measurement, because ruler B has smaller tick marks, it has a higher degree of precision. I'm looking right here. I know the 1 for certain. And if I look closely now, because of the tick marks, I can see it's actually between 1.2 and 1.3. Okay, so that means when I write down 1.2, both of those are now certain with ruler B. And because it's an analog measuring device, you should always make an estimation at the end. Okay, so now if I say 1.25 meters, that 5 is now uncertain. Okay, so here the uncertainty I would say is in the second decimal place. Here the uncertainty was in the first decimal place. Okay, so this is a situation where we have the exact same object, but based off of how we're measuring it, okay, that determines how sure we are about the final result because of our measuring device. And what decimal place we have knowledge of the uncertainty in. Okay, so pause there if you need to look at that some more. Okay, so what I would say is that with an analog measuring device, you should always start with writing your certain digits, and then you should make an estimation to the best of your ability, the uncertain digit. Okay, now there's no right or wrong when you make an estimation. Well, I shouldn't say that. You can do a really bad job making an estimation, but as long as you make a good faith effort on the estimation, that should be sufficient. Okay. What you would say though is that you are uncertain about that last estimation, and we'll talk later about how you express that uncertainty. Okay, but it's going to be with a plus or minus symbol. On the last example we did, I would say that the uncertainty was for ruler A was in the first decimal place. Okay. Because of 1.2, we were estimating on the 0.2, and ruler B should have had an uncertainty in the second decimal place. Okay, because ruler B, we had two numbers that were certain, the 1 and the 0.2, but the 0.05 was uncertain. Okay, so that is making measurements with an analog measuring device. Now, with a digital measuring device, remember, a digital measuring device is one that uses electronics to somehow give you a measurement. And a digital measuring device is only good to the last Sig Fig, okay, the very last decimal place. So for example, if I'm looking at a meter, this is called a voltmeter, and let's say this type of meter, it's reading 0 right now, but let's say it reads 12.1 volts. There is no estimation. You do not make an estimation on a digital measuring device. What you would say is that the very last number, whatever decimal place it is the uncertain one. Okay, so here, based off of how this meter is drawn, I would say the 0.1 is uncertain. Okay, now if you had another measuring device, let's say a stopwatch, and it said, I don't know, 0.619, let's say this is from a stopwatch, so it's in seconds, then again, because it's a digital measuring device, you don't make any estimations, and the last number is where the uncertainty lies. Okay, so that's the difference between an analog and a digital measuring device. Okay, so pause there if you need to finish writing in your notes. Okay, so we're only briefly going to talk about Sig Figs. Sig Figs, or what they call significant figures, are the reasonable number of digits that a measurement or calculation should have. And when I say should have, I mean based off of the precision of the measuring device. So before we saw a red line being measured with two different rulers, and based off of which ruler we used, that determined how many digits our value should have. Okay, the number of significant figures in a calculation reflects the precision of the least precise of the measured values. Okay, so what I mean by that is, let's say we used ruler A to make a measurement, and let's say we had, I don't know, a square, and we used ruler A to measure the length of each side, and we got 1.2 meters, and we got 1.2 meters. And if I asked you to find the area, what you would do is you would do 1.2 times 1.2, I don't know why I put parentheses here, and that would be 1.44 square meters. But the way you would write that is you would write that as 1.4 square meters, because each of these numbers has two sig figs, and the rule when you multiply or divide that you hopefully learn in chemistry is that when you multiply or divide, you keep the smallest number of significant figures. And the reason you do that is because, remember, each of these measurements, that 0.2 was uncertain. So this 0.2 is uncertain. This 0.2 is uncertain. If I were to write down 1.44, now all of a sudden my uncertainty is in the second decimal place rather than the first. Okay, so in other words, I would be saying that I somehow have a better knowledge of my answer just by multiplying two numbers. And of course, that doesn't make sense. You can't multiply two numbers together and have, a less certain answer. If anything, it should be, a less uncertain answer. If anything, when you multiply the 1.2 and the 1.2, the answer that you get should be less certain because each of these has their own estimation tied to it. Okay, so that's why you would write it like 1.4 instead of 1.44 because of Sig Fig rules. And that's why you have the Sig Fig rules, in case you ever wondered why that was a thing. It's so that when you're doing calculations, you basically don't end up lying about how well you know your measurement to. Okay, so pause there if you need to look at that some more. There are rules for doing Sig Figs. I'm not going to go on about this because most of you should know about Sig Figs already. You're welcome to add these to your notes if you would like. But again, most of this should be things that you are familiar with. I will just say that my own personal rule for dealing with Sig Figs is to start with the left farthest value. Okay, and if you go from left to right, whenever you hit a number that is not 0, you start counting, and everything to the right of that is significant. Okay, so for example, if I look at this one right here, 4 does not have a 0 in it. Okay, that means everything to the right of it should be significant. So this has 3 sig figs. 0.75, I don't start counting here because this is 0, but I do start counting at the 0.7, and so everything after the 0.7 should be significant. Okay, so that's 2 sig figs right there. Okay, so pause there if you really need to look over that. You can. I am never going to emphasize sig figs a lot, just because it's not something I like to emphasize, and that's not to say it's not important that you know about Sig Figs. It's just not something that is assessed a lot on the IB exam. Okay, typically not more than 1 or 2 questions per year. Now, I will show you an example of an IB question over Sig Figs, but for the most part, that's something that you should already be familiar with. Okay, so this question right here is from a past IB exam. This is taken from the IB exam about 3 years ago. And the question said, how many significant figures are there in the number 0.0450? And remember what I said is if you start left to right, you don't start counting until you get to the first non-zero number. Okay, so see if you can figure out how many sig figs there are in this number. Okay, so hopefully you figured out that there's 1, 2, 3 sig figs, and so the answer here should be B. Remember, if it comes after you start counting, even if the number is 0, okay, it's still significant. Okay, so the answer here is B. Okay, so let's move on. Let's say I gave you this picture. Actually, we've kind of done this before. But let's say I gave you this picture, and I asked you how long this line is. Hopefully you would realize that this is an analog measuring device. And so you would look at this picture and say, okay, I know the 1 for certain. Okay, there's 1 centimeter right here. This is 1.1. This is 1.2. Okay, and the line, the blue line, is somewhere between 1.2 and 1.3. So the 1.2 is certain, and then I need to make a good, reasonable estimation on the last one. And I think a good, reasonable estimation would be 0.07 or maybe 0.08. Okay, so I look at that, and let's say I write down 1.28 centimeters. Does that mean if you wrote down 1.27 centimeters, does that mean that you're wrong and I'm right? No, of course not, because no matter how you look at it, that last decimal there is uncertain. Okay, and so we talked about that before. We'll just do one more example with this. Actually, let's skip this one. It's kind of hard to read on your screen. But let's get into how you represent uncertainties. Okay, so what is this uncertainty thing? So when we talk about uncertainty, we're basically talking about a range of possible values that hopefully the true value lies in between. And the way you represent that is with what's called a plus or minus symbol. Okay, so the uncertainty in a measurement is a numerical indication of how far off your recorded answer might be from the true value. Okay, and again, that's where you use the plus or minus symbol that you see right there. There's different ways to determine experimental uncertainty, but a lot of the time it comes up to you, the person doing the experiment, to give a reasonable estimation of your own uncertainty. Now, in some classes they teach that you should use half of the smallest tick mark as your uncertainty. Okay, and that is a reasonable place to start, but at the end of the day, it is up to you to come up with some uncertainty that is reasonable for the purposes of the IB exam, as long as you can give a good explanation as to why you chose something to be your uncertainty. That's usually fine. Okay, so let's give an example of what this looks like. Okay, so going back to this line, we did this line before, but this is the one that was between 1.1 and 1.2, and so the 1.1 was certain, and then we made an estimation on the last decimal place, and we got 1.18 centimeters. Now the way I would express the uncertainty is I would say plus or minus, and then I would write my uncertainty. Now again, you should choose something that is reasonable, as long as it's correct, because basically what you're saying when you write down your uncertainty is you're saying I guarantee 100% that the true value is somewhere between this number and this number. So for example, if I write down 1.18 plus or minus 0.05 centimeters, I'm saying, as the person doing this experiment, that the true value is somewhere between 1.13, okay, that would be 1.18 minus 0.05, and 1.23, which is 1.18 plus 0.05 centimeters, and I'm guaranteeing with my life and my honor that the true value is somewhere between those two numbers. Okay, I bet $1 billion on it. Okay, that's how sure I am. That means the uncertainty in an ideal situation, you don't want the uncertainty to be too small, because if it's too small, then you cannot say for with 100% confidence at some point that the actual value is between that range. Okay, so let's see if this is a reasonable uncertainty. If we use 0.05 as our uncertainty, that basically means that the size of the blue line is somewhere between here and here. Okay, and so here you can see that that is a reasonable uncertainty to have used, because I can say with complete confidence that the length of the blue line is between those two marks. Now in reality, could we have chosen a smaller uncertainty? Could we have shrunken that red box and still have been correct about the length of the blue line? Yes. Okay. Realistically speaking, I think we could probably get down to 0.03 centimeters if we wanted to. Okay, so one thing you have to do as a scientist is, come up with a reasonable uncertainty that's not too big, because if it's too big, then, people don't believe you. And if it's too small, then you also have to worry about people not believing you, because the uncertainty is too small. Okay, and so a lot of the times it's just a judgment call. Half of the smallest tick mark is always a good place to start from if you're not sure about the uncertainty then. Okay, so 0.05 centimeters is perfectly fine for this measurement. Okay, but again, sometimes it comes down to making a reasonable judgment call. Okay, so let's see another example. Okay, so here, this is from a past IB exam. It says the diagram below shows the position of the meniscus of the mercury in a mercury in glass thermometer, and they ask us to measure the length of the line. And the answers are already on the screen, so I'm gonna kind of erase that just so you can see what it looks like without all of that on there. But what we can see is, okay, I know for sure it's between 6 and 7, because 6 is here and 7 is here. So I can write 6 down with complete confidence. Now this is an analog measuring device, and so I have to make a reasonable uncertainty of the size of the meniscus. Now it's past 6.0. I would say it's maybe 6.1 or maybe 6.2. Okay, so let's say I say it's, I don't know, 6.2. If you had said 6.1, I couldn't hold that against you. Okay, but now it comes down to the uncertainty. How far off might we be? All right, well, if we say plus or minus 0.5, 0.5 would be between here and here. Okay, which is not necessarily wrong, but we can maybe do a little bit better than that. We can shrink the size of those two lines. And so the accepted answer on this question was C, plus or minus 0.3 degrees Celsius. Or, 0.2 degrees Celsius. Okay, now this is a multiple choice question that only had one correct answer. If you were doing this on your IA or on an actual experiment, would it be wrong to say plus or minus 0.3 or plus or minus 0.4 or plus or minus 0.5? No, it wouldn't necessarily be wrong. But again, you always want to try to minimize your uncertainty if possible. Okay, so here you can see the answer that they had. Okay, so I'm going to stop it right here. In the next video, we'll do a few more examples with this, and then we will move on to talking about accuracy and precision. Please let me know if you have any questions, and as always, I will see you guys in the next video.